lecture, I have discussed about the theoretical understanding of the principal component analysis, and in that video, in that lectures, I have mentioned all those things. But you look, one thing here is that after finding out the eigenvectors, we should normalize. I have mentioned in my previous lecture that we should normalize it, and after normalizing, we have a vector, that is normalized vector for lambda 1, that is for eigenvalue 1, and for eigenvalue 1 means, in my example, that is two variables, so there are two eigenvalues, two latent roots, two characteristic roots. So these roots, that is you can say that the normalized vector, it may be represented by e1, for example, and for higher value of lambda, it would be the first principal component, as I have mentioned in my previous lecture. And so that e1 should have values, and that values, for example, 0.90 and 0.71, for example. So we put this value 0.90. If it is 1, then 0.90 is here, and if I draw this line in this way, and another point is the minus 0.6, so minus 0.6 would be here, 9.9 minus 6, this point. Okay, and now I draw a line passing through the origin, okay. So this is the E1, normalized vector. And now for lambda 2, we have another normalized vector, that is E2, and for E2 we have two values, and for example that values is 0.8 and 0.7, and for example, and 0.8 is here and 0.7 is supposed to be here, this point. Okay, this point, I can mark it in this way, this point. Now from this point I draw a perpendicular through the origin on the E1. Okay, this is the principal component E2. This is E2. So this is the understanding I have mentioned in my previous lecture, but I did not draw this diagram. So I have drawn here and presented you what is the normal or you can say standardized vector. Now, after calculating the values of principal component 1, and there will be some values, and with an example we would clear it, and that points will be placed on E1. Will be E1. Okay. So all those things what I have mentioned up to now will be solved in my example that I am going to present now. Now, before deal with an example, I would like to shed some light on the eigenvalue, eigenvector, and you can say the basic idea of these things, basic ideas and the fundamental ideas or I would like to living these things in front of you. Now, in my example, there are two variables and that variables in the two-dimensional space. If there are 3 or 4 or 5 variables, then it would be 3 or 4, 5 dimensions. And there is an example, there is an examination, and in that examination, some students got involved and they obtained some marks, as I have mentioned. So, in English, the boy, a particular boy in a school, got, for example, 50 marks, and he got 70 marks in that examination in statistics. So this is 50 and this is 70. Okay, 70. So here is a point in the two-dimensional space. And now if you join a line with this point, then this line is nothing but the vector. Nothing but the vector. And this vector can be stretched upward, or it can be shortened. It can be shortened by the eigenvalue. And in this space, there are so many points in this way, as I have mentioned. All the points are not similar to each other. So these all points represents a vector. Represents a particular vector. Okay? Represents a particular vector. Now, so there are so many vectors. So this is nothing but the vector space. And this is the vector space. Now, what is the eigenvalue? Eigenvalue is nothing but if you multiply a linear combinations with the vector, then we get the same vector but multiplied with a scalar number. For example, as I have mentioned, a linear combination A, and this is the vector, and lambda x, then this lambda is the eigenvalue. It is a scalar. It is a scalar thing. And what is the vector? What is the eigenvector? An eigenvector is a vector. Eigenvector is a vector that can be multiplied by a linear combinations of equations, or you can say the matrix. You can say the matrix, and you get the vector extended, or you can increase the vector proportionally or decrease the vector proportionally. There is no change in the direction of the vector. There is only change in the length of the direction, not the direction. For example, suppose here is a tree. Here is a tree. Okay, here is a tree, and this tree, and here is a vector, and here is a vector. Two vectors, horizontally and vertically. Two vectors. So now there is another tree that is like this. Okay. There is another vector, and this is the so between these two between these two vectors, this vector does not change. Between these two vectors, this vector does not change the direction. This vector changes the direction. Change the direction. Look at this. This vector changes the direction, but this does not change the direction. And this is the understanding of the changing the direction of the two vectors. Now, I would spread some light in the particular example so that principal component analysis will be very, very clear in front of you. Now, this is an example, okay? And this example is related with the principal component analysis. And here you are asked to reduce the dimension from 2 to 1, because here we have two dimensions, because two variables are there, and one variable is statistics and another is English, and there is an examination. In that examination, out of 10 marks, 6 students obtained these marks in statistics and English. Okay, so you have asked to reduce the dimension from 2 to 1. And if you have asked in such a way, then it is nothing but the principal component analysis. And for solving this problem, we have to follow these 5 steps. The first one is the step 1, that is the data set. And step 2, the computation of mean. And step 3 is computation of covariance. And step 4 is eigenvalue, eigenvector, normalized eigenvector. And step 5 is derive new data set. So by using these 5 steps, we are going to solve this problem. First is the data set. So that in the data set there are 2 variables. It means small n equal to 2. And there are samples 1, 2, 3, 4, 5, 6. 6 samples, 6 students, 6 individuals are there. So capital N is equal to 6. And this is the data set. Now you have to find out the next computation of mean. Mean, as I have mentioned in my theory, there is a projections of all the points on the horizontal axis as well as the vertical axis, and we have to take the mean of these projections. So in statistics 1, 2, 2, 6, 5, 8, we have to find out the mean of these, and the mean of these is nothing but 4, and mean of English is nothing but 3. 15, 16, 17, 18. So 18 divided by 6 is nothing but 3, and 8, 10, 10, 16, 17, 18, 19 and 24. 24 divided by 6 is nothing but the 4. So this is also the mean. These two are the mean. So step 1 and step 2 has been solved here. Now we will follow the step. The third step is the computations of the covariance matrix. Because for analyzing the principal component analysis, we have to construct the covariance matrix. And this is the covariance matrix: covariance XX, covariance XY, covariance YX, covariance YY. This is the 2 into 2 square matrix. Okay, so X is nothing but the statistics, and Y is nothing but the English. You can say it this way. So statistics and statistics covariance means covariance XS means nothing but the variance, and the formula is 1 by n summation xi minus x bar. X bar is the mean whole square. In the same way, you can find the covariance of YY, that is the variance of Y. And covariance of YXY and covariance YS is the same thing, because there is just the interchange of the place. And covariance XY, the formula is 1 by n summation xi minus x bar yi minus y bar. By using this formula, we are going to find out the values of this matrix. Okay. Now we are computing the values of this matrix that I have mentioned. So covariance of xy, as I have mentioned, covariance of yx are the same. So covariance of xy is, there is 1 by n is the formula. So 1 by 2 third bracket, 1 minus 4, its mean is 4 and its mean is 3. So this is nothing but the mean. Okay, mean, this is 4 and 3. So 1 minus 4, 1 minus 3 plus 2 minus 4, 2 minus 4 multiplied with 1 minus 3 and plus 2 minus 4, 1 minus 3 and 6 minus 4, 5 minus 3 plus 5 minus 4, 5 minus 3 plus 8 minus 4 and 5 minus 3. So by solving this, very simple, class 10 standard, you know. So by very simple, you can, by solving it, you can get the result 40. For making the video or lecture short, I have take the shelter of this part. So now variance of x is that 1 by 2, 1 minus 4, 1 minus 4 whole square, 2 minus 4 whole square, 2 minus 4 whole square, 6 minus 4 whole square, 5 minus 4 whole square, 8 minus 4 whole square. So after solving this, the variance of x is 30. In the same way, the variance of y is 12, that is 1 by 2, 1 minus 3 whole square, 1 whole square plus 1 minus 3 whole square plus 1 minus 3 whole square plus 5 minus 3 whole square plus 5 minus 3 whole square plus 5 minus 3 whole square. After solving, we have the variance of y 12. As the variance of xy is equal to the variance of yx, so the covariance of yx is 40. So we have the 4 elements of the matrix, and by putting the value, we get the covariance matrix of this problem. Okay, now we have to find out the determinant of A minus lambda I, and it should be equal to the 0, and as I have mentioned in the theoretical analysis. And now matrix A is nothing but this and minus lambda. This is the identity matrix, multiplied with the lambda, we get this portion. And after subtraction, matrix subtraction is there, and we have this one. Okay, and now you have to find out the determinant of this, and you should multiply this one and taking the minus sign between the two, and we get this single equation. After solving this equation, we have lambda square minus 25 lambda plus 40 equal to 0. And solving this quadratic equation, we get lambda equal to 23.28 or 1.72, and by using this formula, that is b plus minus root over b square minus 4ac 2a, and as you know, ax plus ax square plus bx plus c. If you follow this formula for the quadratic equation, we can have for the two values and b plus minus and this formula. By using this formula, we can have the value of the lambda, and this is the lambda 1 and this is the lambda 2. And now the lambda 1 is the first principal component because the value of lambda 1 is greater than value of lambda 2. Now we are going to find out the eigenvector. Okay, so eigenvector, you know, here v is the vector, the eigenvector, and we have this equation as you know in my theoretical analysis. So a minus lambda I multiplied with v equal to 0, and from this we have this equal to 0, and this v means v1 v2 vector, and this is the statistic and this is the English, and now this is the matrix, you know, and the same things. And now you can say or and matrix multiplication, we have this equation 1, and we have this equation 2. It means the 14 v1 plus 12 minus lambda v2 equal to 0. And from equation 1 we have 13 minus lambda v1 equal to 14 V2 and V1 by 14 equal to V2 by 13 minus lambda equal to K. So if K is equal to 1, then V1 is equal to 14 and V2 equal to 13 minus lambda. And in this way, we have the values of the two vectors. Now we are going to find out the real values of the V1 value. Eigenvector V1 of lambda 1 and eigenvector you can say, and this is the 14 minus 13 by 14 13 minus lambda 1, and putting the value of lambda 1 we have this. Okay, this is the eigenvector V of lambda 1, and now the eigenvector V for lambda 2, we just put the value of lambda 2 that we have already got. So 14 13 minus lambda 2, and after calculation we have 14 minus 11.8. And now we are, look, these values are not equal to 1 or less than 1, so we have to normalize it, and this value should be within 1. So therefore, now normalizing the eigenvector V E1, that is 14 root over the 14 square plus minus 10.28 whole square, and minus 10.28 divided by root over 14 square plus minus 10.28 whole square. After calculation, we have 0.79 and minus 0.56. This is the normalizing eigenvector V for E1, and in the same way we have E2, the value is 0.78 and 0.62, and these calculations I have done already, so just I have put the value here. Okay, now we have the normalized eigenvector E1 and E2, and now we put the E1 values in this diagram, and these are the points. We are measuring the English here and we are measuring the statistics here. So the 0.79 here, if it is 1, 0.79 is this, and minus 0.5, it is 1, then this point. So we have this point. So we draw a line passing through the origin and this point. Okay, this is the E1 vector. Now for E2, 0.78, 0. This one, and 0.62 this. Here is the point. This point is the 0.78, 0.62. Now we draw a perpendicular on this E1 through the origin, and this is the E2. Okay, this vector is E2. So now we have this E1 and E2 vector on this two-dimensional space. So now, as it is given in our problem, that is, we have to reduce the dimensions of the given data set. So we have to find out the principal component 1, the values of the principal component 1. So values of the principal component 1 we can write in such a way that PC1, and the values are P11, P12, P13, P14, P15 and P16. So we have to find out these values, and the procedure for finding out these values I have already found out or calculated. I have already calculated, and that is the E1, the P11 is nothing but the transpose of the normalized eigenvector, and the value, the marks obtained by the student in the particular examination in English and in statistics, and we have to subtract the mean from the value, and of the corresponding mean, that is mean of the statistics is 3 as we have calculated, and mean of the English is 4. So after we have to calculate, we have to subtract the means from their corresponding values, and after taking the transpose of these and making the calculation, we have the value minus 1.25. In the same way, look, P12 is the E1 vector and transpose of the E1 vector, and now 2 minus 4, 1 minus 3, and after calculation 0.64, and P13 is 0.79, this vector, transpose of the E1 vector, and the corresponding marks obtained by the students and subtractions of their mean, corresponding mean, and we have minus 0.46 after calculation. And in the same way we have found out P15, and P14 is 0.46, P15 is minus 0.33. And P16, the transpose of E1, and 8 marks obtained in English minus the mean, and 5 marks obtained in statistics and minus the mean. And so after calculation we have 2.14. So these are the values. So P11, P12, P13, P14, P15 and P16, we have got all those values. And now up to this we have reduced the 2 dimension into 1 dimension, and now we put these numbers in the E1 normalized vector, principal component 1, and suppose this is minus 1.25. So minus 1 point, this represents the positive E1, this is positive E1, E2, and this is minus E1, this is minus E2. Okay, so E1 is minus 1.25, so near about here, this point, minus 1.5. Minus 0.6 is below this point, okay, and minus 0.6 is the same point, and 0.46 and right to the origin, and but less than the 1, and minus 0.33 also this just above the origin, and plus 2.14, and this point is plus 2.14. This is 1, this is 2.14. So we have plotted all the points on the E1 normalized vector. So this is the principal component analysis, and with this example I have tried my level best to clear the principal component analysis theory as well as the application of the theory in a mathematical problem, so that you can digest it very well. Thank you for enjoying.